Okay, we're going into air pressure, and we're going to discuss why air pressure is important, particularly the significance of why it's changing, both in the vertical and in the horizontal. So yes, we're going to be looking at three dimensions here over time. So what is air pressure, I guess, should be what we ask first. Defining it. Air pressure is a force. Air exerts a force on any object it touches. So believe it or not, you have a force weighing down on your body from air pressure. Because the air molecules are in random motion, they're hitting each other, they exert a force since they collide with other molecules. So the total air pressure is this cumulative force. And because of Dalton, we know that each individual gas in the atmosphere that makes it up has its own pressure. But the total of them, the total air pressure that we want to deal with, is just the sum of all those gases, all their pressures. So, because air pressure is influenced by the molecules moving and gravity pulling the weight of the air down, so weight equals mass times the acceleration of gravity. And guess what? You actually have a pressure on you at all times of 14.7 pounds per square inch. Think about that. That's per square inch. So why don't we all collapse under that weight? Well, guess what? Everything has air pressure inside of them that balances that pressure coming outside. So if you ever watch air being pumped out of something, you see it collapsing inward more and more. That's that air pressure that's around it, pushing it in. There are different ways to measure air pressure. One of the older ways, and the original one, was a barometer. We used to put mercury in a barometer. Mercury's not a nice thing to deal with, so we don't do that anymore. But a mercury barometer, if you have a vacuum in a tube, air pressure pushing down on the weight on that mercury would lift it up into the tube, and you get air pressure. And here's some different units of air pressure. I like dealing in millibars. Basically, reason is that it makes the math much simpler when I'm working. But I bet all of you have heard inches of mercury. And the reason you're hearing that is we're an English unit country. And inches of mercury is an English unit. And most home barometers measure in inches of mercury. They convert it to that. So when a newsman gets on the TV to talk about things, he's going to typically talk in inches of mercury. An interesting thing about air, it's compressible. What does that mean? Well, the further up in the atmosphere, the more further apart the air molecules are, and the less pressure there is. So as you go down closer to the Earth, the air from above has been pushing down on that, pushing the molecules closer and closer together so that there's more molecules in one area near the surface. An example of this might be if you hiked up on top of a tall peak, say a 10,000-foot mountain. Well, when you do that hike, you'll notice if you started at sea level and went upwards, the further up you got, the tougher it got to breathe. Well, the air was compressed. You have less air up at that elevation than you had down at the ground. And we talk about profiles of air pressure in standard atmosphere. Basically, the standard atmosphere is somebody has done a lot of averaging over time to adjust what the actual state of the atmosphere should be for various latitudes and seasons. Here's the horizontal change in air pressure. One of the things I want you to take away from this course is that air pressure decreases in the vertical a whole lot faster than it does in the horizontal. You'll notice here in the horizontal, at one location, a low went by and the pressure dropped down to about 1,007 millibars and then went back up over time. Over about 14 to 15 hours, it went back up to about 1,018 millibars, 1,019 millibars. So you have a change of maybe 13 millibars there. If you go in the vertical, and we'll say 1,000 millibars represents the surface of the Earth. If you went up 150 millibars to where the pressure is 850 millibars, you have now covered about 5,000 feet, not even 1 mile. So the pressure drops 150 millibars in a mile. Really tight pressure gradients in hurricanes might drop 20 millibars, maybe over the course of 50 miles or 100 miles. So you can see much faster drop in the vertical. Also, it tends to be clear when we have high pressure and cloudy when we have lower pressure. Another thing that causes air pressure, related directly to it, is air temperature. So if you increase air temperature and you're not outside, the atmosphere is not a closed container, you're going to push the molecules further apart. You're going to get less dense. There's more molecules in one area, it makes them denser. The pressure will actually drop because of that heating. If you hit a baseball in summertime, when it's really, really hot outside, the air molecules are actually further apart. You think, oh man, that ball's not going to go out of here. But yes, there's a better chance for the ball to go out in the hot summer than in the cold weather in the wintertime. We represent 500 millibar surfaces where about half the atmosphere is above and half is below. The colder it is, that surface is going to go closer to the Earth. The warmer it is, the higher up that surface is going to be. So in the wintertime, the 500 millibar surface is going to tend to be closer to the ground. In the summertime, it's going to tend to be further away. Oh yeah, humid air is actually lighter than dry air and less dense. So the more moisture in the air, the lighter that air is. Again, decreasing air pressure. So why does air pressure change besides just that temperature thing? Well, winds blow. So if the winds are converging, the air is coming together, it's going to make the air denser. So we're forcing the air to move. If the air can't go anywhere, the air pressure would go up. But if the air can go somewhere, and say you have divergent air at the bottom of a column of air and convergent at the top, well, that air is going to be pushed down. Those molecules are getting pushed to the surface. What happens? The air pressure goes up. If the opposite happens, if you had convergence at the bottom and divergence at the top, the molecules are getting pushed upwards. So the air pressure actually goes down. The ideal gas law is a very simple relationship between pressure, temperature, and density. If you know 2 out of the 3, you can calculate the other. So we just talked about the air spreading apart as you go up. Well, if you let air out of a tire, did you ever feel how cold it gets? Or if you're putting air into the tire, did you ever feel how warm that air is making the pump surface? So in the atmosphere, if air is rising upwards where it's going to expand, the air parcel is going to cool. If the air is being pushed down, it's going to warm. So if the air is compressed, energy is used to do that work. So the air parcel heats up. It gained energy. If the air expands, the air does work on its surroundings. It's pushing apart. It's losing energy. And here we can actually calculate what we call the adiabatic lapse rate. If you did a calculation, we would find that air temperature decreases 9.8 degrees Celsius per 1,000 meters, or roughly 5.5 degrees for every 1,000 feet. So if you climb a tall mountain, guess what? The air temperature is going to drop as you're going up, all because of this adiabatic process. Now, moist adiabatic lapse rate is a whole different thing. Air parcel becomes saturated. Latent heat, we've talked about that earlier in changing temperature. Latent heat is released, warming the air so that a moist adiabatic lapse rate does not cool as fast as a dry adiabatic lapse rate. There's a variation going on there. So let's take a look at this in real time, just a couple of slides here. Here is what I would call an atmospheric sounding. It's for Blacksburg, Virginia today. And on the left-hand side are pressures. The plotted red line is temperatures. And guess what? The temperatures are slanted to the right. So here, for example, is a minus 10 degrees. It goes this way. So if I was plotting minus 10 at 500 millibars, I would be plotting it right about here somewhere. And guess what? It's pretty close to what it is, actually. But you can see the temperatures cool with height fairly quickly. Now, plotted right next to it is a moist adiabatic lapse rate. So, if the air parcel got saturated, it would be going up the temperature in that air parcel on the moist adiabatic. So it would be warmer than the dry adiabatic lapse rate. This just gives you an example of how temperature changes with height. And we never get moist adiabatic lapse rate or dry adiabatic lapse rate. There's always outside influences on it that impact it. But this is actually a very sounding that is very conducive to severe weather. And if I get it up here, here's a surface pressure map, and I wanted to just show you the pressure gradient. This is a 989 millibar low east of Hudson Bay. Cold front coming down through it here, stationary to warm front up in here. Pressure. On a station symbol, the pressure is in the upper right-hand corner. So, 897. In this case, the pressure is above what I would call 500. If that number is above 500, I'm putting a 9 in front of it. So it's 989.7 millibars. That is that station pressure. Over here, it's 122. So I'm putting a 10 in front of that. So it's 1012.2 millibars. And you can see the millibar lines, isobars that we've learned how to draw are right there. So this gives you a little bit of an idea on pressure. I hope you got something out of it.